This is Digital Technologies 1, from the Toptronic College. Topic 1, the base numbering system. Reference card for Lesson 3. About the hexadecimal numbers. Using hexadecimal numbers can be convenient because they take less space on paper to be represented. Just imagine a long serial number in binary or even decimal. That could be exceptionally long on a sticker. For example, check the device ID or product ID number of your operating system. It is likely that that serial number is shown as a hexadecimal number. Let us take the end of the device ID number and convert it to binary. It became so long that it would be easy to make a mistake when trying to use it on paper for our own use and understanding. The left side of the equation is the hexadecimal number. The right side of the equation is the binary equivalent. The decimal number is also longer than the hexadecimal. If we add more numbers to the hexadecimal, it becomes clear of its advantage, compared to the use of binary numbers or decimal numbers. Hexadecimal numbers are represented by the decimal digits 0 to 9, and the letters A to F. In hexadecimal, the numbers from 0 to 9 are the same as in decimal. But the number 10 decimal become the letter A in hexadecimal. The number 11 decimal become the letter B in hexadecimal. The number 12 decimal become the letter C in hexadecimal. The number 13 decimal become the letter D in hexadecimal. The number 14 decimal become the letter E in hexadecimal. The number 15 decimal become the letter F in hexadecimal. The main reason for using the hexadecimal numbers is because it is easier for programmers, and the space in the coding is more manageable. Hexadecimal numbers are also in direct relation with binary numbers, because one hexadecimal number is exactly 4 bits in binary. A 4 digits hexadecimal number is represented by 16 bits. It is easier for a programmer to deal with 4 hexadecimal digits instead of a 16-bit number. Hexadecimal numbers are base 16. The hexadecimal range number is therefore 16 exponent n-1. Hexadecimal number, for example the number 123 hexadecimal, have their base 16, sometimes written as a subscript number 16, as in 123 base 16, or as a subscript letter H, as in 123 base H, or some programmers use the subscript letter X, as in 123 base X. We have seen that, in the hexadecimal numbering system, each number from 0 to 9 and letters from A to F could represent an equivalent decimal number up to 16 combinations, including the 0. We have seen that, in the hexadecimal numbering system, each column of the hexadecimal number has 16 times the weight of the previous column, and the hexadecimal numbers are referred to as a base 16 numbering system. For example, the range of the first column is 16 exponent n-1. In our case, n is equal to 1. This is the first column, and this is what we use for n. This makes 16 exponent 1-1 equal to 15. The first column can have a decimal number from 0 to 15 represented by an hexadecimal. In this case, the least significant digit is also the first column. We also have seen, hexadecimal numbers can be written as 1234 base 16 or 1234 base H or 1234 base X. If you were to represent the decimal number 230 in hexadecimal, what would you get? 230 base 10 means, this is a decimal number with the value of 230. But because, generally, we do not mention the base 10 as this is the system we all use by default. In hexadecimal, the decimal number 230 would be made of 2 hexadecimal numbers. The LSD would be of a value of 6, and the next digit would have a value of E. That is because 230 base 10 equals E6 base 16 equals E multiplied by 16 exponent 2 plus 6 multiplied by 16 exponent 1. So, when writing software, it is likely that the value 230 volts is defined as voltage equals E6 base H or voltage equals E6 base X, or voltage equals E6 base 16. It is easier than to write voltage equals 111001110 binary, or voltage equals 111001110 base 2, and it is easier for the programmer to remember the hexadecimal value than the binary value.